Hello, everyone. Today we're embarking on a cosmic journey, a detective story billions of years in the making. Our destination? Understanding how that big, beautiful, silvery moon hanging in the night sky came to be. It seems so familiar, so constant, yet the story of its birth is one of colossal impacts, swirling debris and gravitational dances. It's a tale that begins with the very formation of our solar system, and ultimately, the creation of our own planet, Earth. So buckle up, because we're about to dive into the amazing and sometimes violent history of our moon. If you enjoy this journey, consider hitting that like button and subscribing for more astronomical adventures. What is the very first thing that comes to mind when you think about the moon? I'd love to hear your thoughts in the comments below. Before we can understand the moon's origin, we need a quick refresher on how the solar system itself was born. Imagine a giant cloud of gas and dust, called a solar nebula, swirling in space. Gravity began to pull this material together, causing it to spin faster and faster. At the center, the pressure and temperature became so intense that nuclear fusion ignited, birthing our sun. The remaining dust and gas formed a swirling disk around the young sun. Within this disk, particles collided and clumped together, gradually forming larger and larger objects. These objects, called planetesimals, eventually grew into the planets we know today, including Earth. The leftovers, bits and pieces that weren't swept up, are what we see as asteroids and comets. Now let's focus on the early Earth. Imagine a young planet, still quite molten and very different from the Earth we know today. This early Earth was undergoing intense bombardment from leftover planetesimals, a period known as the Late Heavy Bombardment. Impacts were frequent and colossal, reshaping the surface and injecting vast amounts of energy into the planet. It's within this chaotic period that the leading theory for the moon's formation takes place. The Earth was still forming, gathering up the bits of space rock around it, and slowly getting bigger and bigger and hotter and hotter. The most widely accepted theory for the moon's formation is the, quote, giant impact hypothesis. This theory proposes that a Mars-sized object, often nicknamed Theia, a titaness in Greek mythology, the mother of the moon goddess Selene, collided with the early Earth. This wasn't a glancing blow, but a head-on collision of unimaginable force. The energy released by this impact was staggering. It's almost impossible for us to fully comprehend. The Earth itself was drastically changed by the impact, and a huge amount of material was blasted into space. So what happened after this colossal collision? The impact vaporized a significant portion of both the Earth's mantle and Theia. This vaporized material, along with molten rock and debris, was ejected into space. The key here is that the impact was so energetic that it launched material far enough away from Earth to avoid falling straight back down. Instead, this ejected material formed a disk around the Earth, similar to the one that formed the planets around the Sun, albeit made of much hotter, more violent stuff. This disk of debris, composed of vaporized rock and molten material, wasn't stable. Gravity, as always, played the key role. Over a relatively short period, estimated to be just a few tens of thousands of years, the material in the disk began to coalesce. Imagine bits of dust and rock bumping into each other, sticking together and gradually growing larger. This process, called accretion, led to the formation of larger and larger objects within the disk. As the material in the disk accreted, one object eventually became dominant. It swept up the remaining debris, growing larger and larger until it became the moon. The moon's early surface was likely a molten ocean of magma, constantly bombarded by leftover debris from the impact. It's hard to imagine a world so radically different from the calm, cratered surface we see today. But the early moon was a fiery, chaotic place. One of the strongest pieces of evidence supporting the giant impact hypothesis is the similarity in composition between the Earth's mantle and the Moon. Analysis of lunar rocks brought back by the Apollo missions revealed that they share a similar isotopic signature to the Earth's mantle. This strongly suggests that the Moon formed primarily from material that originated from the Earth itself, which would be expected if the giant impact hypothesis is correct. It's a crucial piece of the puzzle. However, there are some nuances. While the isotopic signatures are similar, they aren't identical. The Moon seems to have a slightly different composition than the Earth's mantle, particularly in terms of volatile elements like water and sodium. This suggests that Theia, the impactor, may have contributed some material to the Moon's formation, or that the extreme heat of the impact caused some of the volatile elements to evaporate. This is an area of ongoing research. Scientists use computer simulations to model the giant impact hypothesis. These simulations allow them to test different impact scenarios, varying the size, speed, and angle of the impactor to see which scenarios best match the observed properties of the Earth-Moon system. These simulations are incredibly complex, requiring massive amounts of computing power. They help scientists refine our understanding of the Moon's formation and address some of the remaining questions. One of the challenges with the giant impact hypothesis is explaining the Moon's relatively small iron core. Compared to other terrestrial planets, the Moon has a surprisingly small core, representing only a small percentage of its total mass. Some scientists believe that Theia may have already had a differentiated core before the impact, and that this core merged with the Earth's core during the collision. Other theories propose that much of Theia's core remained within the Earth. The early Moon was much closer to the Earth than it is today. Tidal forces exerted by the Moon on the Earth were much stronger, causing extreme tides and likely slowing down the Earth's rotation. Over billions of years, the Moon has gradually moved further away from the Earth due to these tidal interactions. This process is still ongoing. The Moon is currently receding from the Earth at a rate of about 3.8 centimeters per year. The Moon's gravitational pull has a significant impact on Earth. It stabilizes our planet's axial tilt, which helps to regulate our climate and seasons. Without the Moon, Earth's axial tilt could wobble wildly, leading to dramatic climate swings. The tides also play a crucial role in marine ecosystems, influencing the distribution of nutrients and the behavior of marine life. The Moon, it turns out, is crucial for life on Earth. While the giant impact hypothesis is the leading theory, it's not the only one. Other theories have been proposed to explain the Moon's origin, although they face various challenges. One alternative is the co-accretion theory, which suggests that the Earth and Moon formed simultaneously from the same protoplanetary disk. However, this theory struggles to explain the differences in density and iron core size between the Earth and Moon. Another alternative is the capture theory, which proposes that the Moon formed elsewhere in the solar system and was later captured by Earth's gravity. However, this theory is unlikely because it would require a very specific set of circumstances and doesn't easily explain the compositional similarities between the Earth and Moon. These other theories still linger in the scientific community, though, and are still explored for any potential bits of insight they might offer. The Moon's surface is covered in craters, scars from billions of years of asteroid and comet impacts. These craters provide a valuable record of the solar system's early history, preserving evidence of the intense bombardment that shaped the planets. By studying the size, distribution, and age of lunar craters, scientists can learn about the frequency and intensity of impacts throughout the solar system's history. The Moon acts like a time capsule in that way. The dark, smooth areas on the Moon's surface are called maria, which is Latin for seas. These maria are vast plains of solidified lava formed by volcanic eruptions that occurred billions of years ago. The maria are primarily located on the near side of the Moon, the side that always faces Earth. This asymmetry is another interesting feature of the Earth-Moon system that scientists are still trying to fully understand. The far side of the Moon, the side that never faces Earth, is significantly different from the near side. It has fewer maria and a much thicker crust. This difference in crustal thickness is another mystery that scientists are investigating. Some theories suggest that the Earth's gravity may have played a role in shaping the Moon's crust, causing it to be thicker on the far side. It remains a bit of a mystery that we can still look up and ponder today. The Apollo missions provided invaluable data and lunar samples that revolutionized our understanding of the Moon. Astronauts collected rocks, soil, and other materials that have been extensively studied by scientists around the world. These samples have provided insights into the Moon's composition, age, and formation, and have helped to validate the giant impact hypothesis. They are still studied to this day. Future lunar missions, such as NASA's Artemis program, aim to return humans to the Moon and establish a sustainable presence there. These missions will provide opportunities for further scientific research and exploration and could potentially unlock new resources. Returning to the Moon will enable us to further study the formation of the Moon, hopefully putting some of these debates to rest and confirming the precise mechanics of how the whole process occurred. One of the key goals of future lunar missions is to search for water ice at the Moon's poles. Permanently shadowed craters near the poles are thought to harbor significant deposits of water ice, which could be used as a resource for future lunar settlements. Water ice could be used to produce rocket fuel, drinking water, and other essential supplies, making long-term lunar habitation more feasible. This could truly open the door to human expansion to the stars. Hey, if you are still enjoying this presentation, consider hitting that like button and subscribing for more space-based content. What do you think the impact of finding water on the Moon would be? Sound off in the comments below. The Moon is not just a barren rock in the sky. It's a dynamic and evolving world with its own unique geological processes. Scientists have discovered evidence of recent volcanic activity on the Moon, suggesting that it may still be geologically active. Understanding the Moon's geological history can provide insights into the evolution of other terrestrial planets, including Earth. It's also a great testing ground for how planetary geology happens. Studying the Moon helps us understand the history of our own planet. The Earth and Moon share a common origin, and the Moon has preserved a record of the early solar system that has been erased on Earth by plate tectonics and erosion. By studying the Moon, we can learn about the conditions that existed on Earth in its early days and how our planet evolved over billions of years. We need to look up to understand what is under our own feet. The Moon is a stepping stone for future exploration of the solar system. It can serve as a base for launching missions to Mars and other destinations, reducing the cost and complexity of space travel. Using the Moon as a launch pad would allow us to utilize its lower gravity and lack of atmosphere to our advantage, making it easier and cheaper to send spacecraft to other planets. The Moon can be the first rung on the ladder. The quest to understand the Moon's origin is an ongoing scientific endeavor. Scientists are constantly gathering new data and refining our understanding of the processes that shaped the Earth-Moon system. Future missions and technological advancements will undoubtedly shed more light on the Moon's formation and evolution, and may even reveal new surprises. We're still just scratching the surface of our understanding. The story of the Moon's creation is a testament to the power of scientific inquiry. It's a story that has been pieced together from observations, experiments, and simulations, revealing a dramatic and complex history. It highlights the collaborative nature of science, with researchers from around the world working together to unravel the mysteries of the universe. The only way we got here was through many working together. The Moon, once believed to be a static and unchanging world, is now recognized as a dynamic and fascinating object with a rich history. From its violent birth in a cataclysmic collision to its ongoing influence on Earth, The moon continues to captivate our imagination and inspire scientific exploration. It is a source of wonder, a reminder of the vastness and complexity of the universe, and a testament to the power of human curiosity. So next time you look up at the moon, remember the incredible story of its creation. Remember the giant impact, the swirling disk of debris, and the slow process of accretion that formed the celestial body we see today. Think about the moon's influence on Earth, its role in stabilizing our climate and shaping our oceans. The moon is far more than just a pretty light in the night sky. The story of the moon's formation is a reminder that our solar system is a dynamic and ever-changing place. It is a story of collisions, mergers, and gravitational interactions, all playing out on a cosmic scale. It is a story that continues to unfold as we explore the moon and other objects in our solar system, pushing the boundaries of human knowledge and understanding. The more we know, the more we realize that there is so much that we don't know. And with that, we've reached the end of our lunar journey. I hope you've enjoyed learning about the fascinating story of how the moon was made. It's a tale of cosmic collisions and gravitational dances, a true epic in the history of our solar system. Remember to like and subscribe for more astronomical explorations. What other cosmic bodies are you interested in learning about? Tell me in the comments. Be curious. Think oddly.